हो भाई झालं चालू करून द्या मला हो Hello, am I audible to everybody? Yeah? Okay. Fine. So, in the last class, we talked about the basic idea of a random variable. So, there are three things involved in a random variable. What are they? One, an experiment which has a chance outcome. Then, a function which assigns real values to the chance outcome. And then, a rule which assigns probabilities to various values of this function depending upon the values which are taken by the various outcomes of the chance experiment. Right? So that's how the random variable essentially consists of these three. Is the idea clear to everybody? So we'll now learn more about the random variable. Okay? So, suppose my experiment is very simple. I have a die. I have a die. I am going to roll the die. And I am going to give you as much money as the number on the uppermost face of the die. Okay? So what's the random variable? The money that you get. In this case, coincidentally, the outcome of the outcome of the chance experiment is also a real number. But I can think of a six-sided cube where the sides are not numbers but colors. And I can say that if you get green, you get 1 rupee, the color is red, you get 2 rupees. Right, so it's not necessarily the outcome of the chance experiment be all real value. The point is I am assigning a random variable which says if the green color then you get this much money. Or if it is 1 you get this much money, 2 you get this much money, 3 you get this much money. So that is my random variable. And then the point now is to assign probabilities to these various values. Right? So now suppose, what are my possible outcomes? This is a set of all possible outcomes. We represent that by omega. Okay? How much money, if you get 1, how much money do you get? 1. So 1. If the outcome is 2, how much money do you get? 2. If the outcome is 3, how much money do you get? 3. If the outcome is 4, you get 4 rupees, 5, 6. So, what are the various values that my random variable will take? Sorry. Yeah, x 1, 2, 3, 4, 5, 6. And I want to assign probabilities to these various values. So I want to find the probability with which x takes the value 1, probability with which x takes the value 2, and so on. What is the probability with which x will take the value 1? Why are you saying 1 by 6? Because there are 6 possible outcomes and all outcomes are equally likely. Okay, that's the next most important line. Because if I have a coin which is not balanced, okay, there are 2 possible outcomes, head or tail, but then 90% of the time it lands heads. Then I have 2 outcomes. But the probability of head and probability of tail are not the same. Right? Okay? So because all the outcomes are equally likely, we have the probability of 1 is this, which is 1 by 6. Okay? P of x. What is P of 2? 1 by 6, 1 by 6, 1 by 6, 7. If I define these random variables differently, okay, for example, if I define the random variable differently, say you get 5 if the number is an odd number You get 3 if the number is an even number. Right? Then this will be 5, this will be 3, this will be 5, this will be 3, 5, and again 3. Right? Okay, so of course x will change. X will then take values 5 and 3. And the probability with which it will take 5, how will you obtain that? When does it take 5? This or this. These are all mutually exclusive outcomes. So we are looking at the probability of A union B union C, which is for exclusive outcomes P of A plus P of B plus P of C, and therefore you will say that is 1 upon 6 plus 1 upon 6 plus 1 upon 6 is 3 upon 6 is half. That's how you think, right? You don't use intuition too much because sometimes intuition can be quite confusing. You can use it for simple experiments. So for more complicated experiments, you have to think like that. Okay, so we have agreed. Now the first thing that I want to introduce to you is the idea of an expected value of a random variable. Okay. So this is x. Now, suppose I did the following. I did 1 into 1 by 6. 1 the value of the random variable, 1 by 6 the probability with which it takes the value. So multiplied plus 2 into 1 by 6, 3 into 1 by 6. What have I done? I have taken each value of the random variable, multiplied that with the associated probability and summed up. Yeah? That object is very important in statistics and we will spend a lot of time learning about it. That object is called the expected value of the random variable. Okay? This value will be called expected value of x. And what would that value be here? Can somebody calculate this?
21 by 6.
21 by 6. So what is 21 by 6? 3.5. 3.5. Okay, it's 3.5. Now this is a fascinatingly interesting number. Let me take you to another example, which is perhaps simpler, but it will help you understand this number better. Okay? So, now suppose we are rolling that, suppose I am tossing the coin. Okay? Suppose I am tossing the coin. The coin can come up what? Heads or tails. Right, so what is my omega? Yeah? Now the rule is, if the coin comes up heads, you give me 1 rupee. If the coin comes up tails, I take 1 rupee from you. So from your earnings point of view, if you get H, what's your earning? Plus 1. If you get T, what's your earning? Minus 1. So your random variable x is now plus 1 and minus 1. Okay? What is the probability with which x takes the value plus 1? 1 upon 2. Why? Both are equally likely. Not only there are 2 outcomes, but both outcomes are equally likely. Right? It's just not because there is 3 outcomes that you see each one the probability 1 by 3. India is now playing the West Indies, right? Okay, so India might lose, India might win, or the match might be draw. There are 3 possible outcomes. But are they all equally likely? No, India is much more likely to win with the current situation, right? So it's because 3 outcomes don't necessarily be equal probability. The structure of the experiment has to be such that they are also equally likely. Okay, so in this case they are equally likely. So probability P of x is 0.5. So what is the expected value of x here? What would that be? Tell somebody each value of the random variable multiplied with the associated probability and sum. So what should I do to find the expected value? 1 into 0.5 plus minus 1 into 0.5 is 0.5 minus 0.5 equal to 0. Let's understand what that means. Suppose I toss 5 coins to you. I toss the same coin 5 times. Okay? Suppose I toss the coin 5 times. Okay? Now suppose I toss the coin 5 times. Suppose the following is the output for you. So first time the coin was tossed, you won. Second time I tossed the coin, you won. Third time I tossed the coin, you lost. Fourth time I tossed the coin, you lost. Fifth time as well, you lost. Yeah? This is entirely possible. So if I ask you to find out what your average earnings in this toss of 5 are, how will you find the average earnings? Sum all these earnings and divide by 5. So what will you do? 1 plus 1 plus minus 1 plus minus 1 upon 5. Isn't this what you do? Okay. Now let me rewrite this a little bit. If I have to rewrite this a little bit, I will write this as 3 times 1 upon 5. Sorry, 2 times 1 upon 5, 2 times plus 1 upon 5, plus 3 times minus 1 upon 5, right? 3 times minus 1 upon 5. Sure? Is this clear? This can be written as 2 upon 5 into 1 plus 3 upon 5 into minus 1. Sure? Which we call the arithmetic mean x bar. Sure? Okay. Now, what is this arithmetic mean? Can you compare this and this? Here also I have multiplied 1 with something, there also I have multiplied 1 with something. But here I have multiplied 1 with 0.5, the probability of getting 1. Here I have multiplied 1 by 2 upon 5. And what is 2 upon 5? The number of times I got 1 divided by the total number of tosses, which is called the relative frequency of 1. Right? So 2 upon 5 here is the relative frequency of 1. 3 upon 5 is the relative frequency of minus 1. So what have I done? What is the difference between x bar and expected value of x? Can somebody tell me the difference between x bar and the expected value of x?
So in the expected value, we expect something to happen, whereas here...
No, just tell me from the formula.
Sir, we say that you already lost the coin 5 times.
Just tell me what is the difference between the two formulae.
The expected value is exactly the finite number of extractions.
Look at the two formulae and tell me what is the difference. In this case, I have multiplied each value of x by its probability and then sum. In this case, I have multiplied each value of x by its relative frequency and sum. So what is the difference between the sample mean and expectation of x? In the sample mean, what I have here is a sample, right? What I have here is really a sample. Sure, 1, 1, 1 and minus 1, just a small sample, right? Out of anything that can happen. So if I toss this, the die again 5 times, will I get the same 1, 1, minus 1, minus 1, minus 1? I might get something else. Right, so what I have really is a sample of size 5. It's a random sample of size 5, which has been drawn from a very large population. If I kept on doing this experiment, I get a large population, out of which I picked up any 5, right? And calculated x bar. Sure. Now, so the x bar, the difference between x bar and expectation of x is when I think of x bar, I am thinking of each value of the random variable multiplied by its relative frequency and then sum. Whereas when I think of expectation of x, I think of each value of the random variable multiplied by its probability and sum. Is it clear? Now, even when the two are different, they are very closely tied together. Because, look at this. We are on the verge of a very, very important idea in statistics. So please think of this idea very carefully. Now suppose I toss this coin so I toss this coin 5 times. 40% of the times I won, 60% of the times I lost. Yeah? I got 2 ones and 3 minus 1s. So 2 out of 5 is 40% of the times I won, 60% of the times I lost. Suppose I toss this coin, say, 500 times. Do you think I still continue to win 40% of the time and lose 60% of the time? No. Then what would happen? Yeah. The frequencies, the proportion of times I win and the proportion of times I lose will start getting closer and closer and closer to 50% or 0.5. Yeah? Which means as the sample size increases, the relative frequencies will get closer and closer to probabilities. As the number of times I toss the coin increases, this will get closer and closer to 0.5, right? This will also get closer and closer to 0.5. Sure? Which means that x bar will get closer and closer to expectation x. Yeah? Alright? X bar is getting closer and closer to expectation x. Right, so we now know what is x bar. Let's try to understand what is expectation x. What is that number 3.5? Okay, what's that number 3.5? So, let me go back to my old, die rolling experiment. And I'm going to abuse notation a little bit. Okay? When I'm a discrete variable, I'm going to draw it as a continuous variable, but that's only for very better understanding, and we'll come back to it when we need to be clear. So think of x. Okay? Yeah? Sure. Now, I have x here, and I have the probability with which x takes various values. Okay? So what is the value? Suppose, does x take a value less than 1? No. So the probability x takes a value less than 1 is 0. Does x take a value greater than 6? The probability x takes a value greater than 6 is also 0. Right. What is the probability with which x takes a value 1? 1 by 2. 1 by. So I need to dot here. 3. 4. Right? Now let me join these dots. I'm not really doing something which is very correct because my x does not really take values between 1 and 2 and so on. Right? It really takes values, but I want to show you something. So now think of this line as a stick hanging over the x-axis. Think of this line as a stick which hangs over the x-axis, the segment. In your 10th standard, you must have learned to find the midpoint of a segment. How do you find the midpoint of a segment? Yeah? So, what do you divide by 2? You add the two endpoints and divide by 2. What's the one endpoint here? 1. What is second endpoint? If you add them up, what do you get? Divide by 2, what do you get? Which was what? Expected value of the random variable. Right? So, the expected value of the random variable in this case is somehow the center of gravity of the distribution. Right? The center of gravity of the distribution. Okay, now why is what we have done very important? Okay, what we have just learned very important? Because think of, suppose you want to understand the average income of a person in Mumbai. Okay? Average income of a person in Mumbai. If you really wanted to arrive at that number, what would you do? So you go to each of the Mumbai person, ask them what their income is, sum all those incomes and divide by the number of people who live in Mumbai. Right? You will get the average income of a Mumbaiker. Right? Okay. What would that be in all probability? The income distribution in Mumbai is something like this. Yeah, if you put income on this axis and the probability with which people earn those incomes on this axis, then there are a lot of people who earn low levels of incomes, there are a lot of people who earn high incomes, the probability is very small and so on. Right, so when you think of the expected value, so if you have a random variable, the income earned by a Mumbaiker is a random variable. In the sense, you pick up a person at random from the population, if you ask him how much income he or she earns, then the number which will differ every time, which will be an outcome of a chance experiment, right? Which will be an outcome of a chance experiment because it will depend upon who you pick up. Sure? Okay, so therefore, the income of a person in Mumbai, when you think of the whole city of Mumbai, is actually a random variable with some probability distribution. And when you say you want to find the average value of income, what you really want to do is find the center of gravity of it. Or what you want to find is the expected value. Right? But can you actually in practice do this? Can you actually in practice do this? No, because there are too many people in Mumbai to be actually counted like this and their incomes to be added and divided. Right? So what will you do? You choose some people at random, call them a sample, and call that number the average income. Right? But is that but there is a difference between the two. The average that you get is based on a small sample. What you want to talk about is the overall average. Right? The two are very different because the overall average is not a random variable. If you have all, suppose you freeze everything else, and if you count all the people in Mumbai and average their incomes, then you redo the exercise again. Do you think you need a different number? You should not, because you are counting the same people all over, right? So therefore, the average income of all Mumbaikars is not a random variable. Right? It's a fixed parameter. It will be some value like say 20,000 rupees, 67 paise and so on and so on. But it is a fixed number. And if you do the experiment again, that number will not change. As long as nothing else changes. Right? And therefore what you are doing is not an outcome of the chance experiment. Yeah? Like for example, if I weigh this chalk, and if I pick up this chalk again and weigh this, and again I pick up this chalk and weigh this, it's not an outcome of the chance experiment, the same number every time. Right? So therefore the actual average income in Mumbai is not an outcome of the chance experiment, and it's not a random variable. It's a fixed parameter. The problem is I can never know that parameter. I can never know it because the information required is too high. I can't really every time, it's difficult for me to, it's impossible for me to calculate that number precisely. So what do? I take a sample. I randomly select 5 people or 10 people or 100 people and average their income. But the point is, every time I repeat this experiment, I will get a different number because every time I choose a different set of 100 people. So my X bar, the sample mean, is a random variable. Right? Whereas what I want to know is not a random variable, it's a fixed number. So the two things are fundamentally different. Right? You understand the difference between the two? It's a very important difference. So why do we take samples? Why do we take samples? What we just did here is very important. It says that even when each x bar that you will get from the sample is not necessarily equal to the population mean that you are trying to estimate, your method of estimating at least has the property that as you keep on increasing the sample size, x bar will get closer and closer to what you want to know. Is this idea clear to everybody? So x bar is, so think of it this way. There is a population parameter which you can never know. All that you can, because the information requirements is simply too high. Right? All that you can do is make a guess. Make a guess. And the sample mean is a guess at what the population value is. Okay? But then there are ways of making good guesses and there are ways of making bad guesses. Some cases can be terribly wrong, some cases can be good. And so we must have some framework to distinguish between what is a good guess and what is not a good guess. So it says that x bar is a good guess in the sense as the sample size increases, you are guaranteed that x bar will get closer and closer and closer to the population mean, the unknown quantity that you want to have. Right? So you might never know what the unknown quantity actually is, but you are guaranteed that you can get closer and closer and closer, right? Okay, to that population mean. So x bar is an estimator. We want to estimate the population mean, which we do not know. X bar is an estimator, that is x bar is a guess. And x bar has an interesting property, a very useful property, that as the sample size increases, x bar will get closer and closer to the population mean. It doesn't mean it will ever touch that. Right? It doesn't mean it will ever touch that. Right? More form